Joule-Thomson coefficient. The objective of this experiment is to quantitatively measure the non-ideality of gases using the Joule-Thomson coefficient and relating it to the coefficient of equation for ideality and the Reynolds-Jones potential. For an ideal gas, the internal energy is only function of the absolute temperatures. So is an isothermal process del E equal to 0. The same is true for the enthalpy for such process H equal to 0. These are the non-zero for a non-ideal gases. The work done by the gases on first work by the gases on the second positions. W1 equal to P1 V1 and W2 equal to P2 V2. The change in internal energy del E equal to minus plus P2 V2 minus P1 V1. The pressure differentiations. Initial volume, initial final volume, initial pressure, final pressure. The internal energy E2 equal to E2 minus P2 V2 equal to E1 minus P1 V2, and therefore we can write H2 equal to H1 for isentropic process. The dH equal to dH divided by dou B, dP equal to OH divided by dou T, dt equal to 0. These are the examples of image of plugs, porous plugs. This is a insulated area, pressure P1 and P2. This can be rearranged to give, we can write in this methods, T by B, H by P pressures, which is 0 for an ideal gases, for a non-ideal gases. dH equal to dds plus VdP and the constant temperature H by P, S by P. Using the two relationships, dou G divided by dou P equal to V, dou G divided by dou T equal to minus S. So we can write dou square G divided by dou B dt, dou V divided by dou dt, dou S, dou B, which upon the substitutions give the Joule-Thomson coefficient for non-ideal gases. We can write by these equations. From the known equations of state, the sign and the magnitude of Joule-Thomson coefficient can be calculated. The van der Waals equation serves as an example. P plus an square divided by V square equal to minus V minus NB equal to nRT, which can be differentiated after neglect of the smallest magnitude term to give. We can write dou V by dou T equal to nR divided by P divided plus Na divided by RT squares, and using the approximations, nR divided by P equal to V minus NB divided by T plus Na equal to RT square leads to dou V by dou T. We can write V minus NB divided by T plus 2Na RT square. So the van der Waals from the Joule-Thomson coefficient is mu Jt equal to 2Na divided by RT minus NB divided by Cp, constant process, with the inversions temperatures T1 equal to 2A divided by RP. If the neglected term is included, exact solutions T2 minus 2A divided by RP Ti plus 3A divided by R square equal to 0. The another equations describe the non-ideality is the Bartlett, the Bridgman's equations. The vertical lines highlighted inversion temperature T1, P horizontal lines mentioned in P atmospheres 100 to 300. This is the experimental details. The van der Waals, the dotted lines is a van der Waals. These are the equations. This give another expression for the Joule-Thomson coefficient mentioned here. These are the equations. The most general equations is the viral equations PV divided by RT, BT divided by V, B3 divided by V, which yields an expression for the Joule-Thomson coefficients. We can write this method as mu is equal to E divided by Cp minus V2. The viral equations V2 can be found from the statical mechanical equation mechanics. These are the V2 T integrations and 0 power of infinity 2 by R dr. The differentiates with respect to the temperatures give the theoretical expression for the Joule-Thomson coefficients that makes it now the function of the potential energy of interactions of the molecules. A common representation of potentials is the Lennard-Jones potential. Thus, the GIT coefficients can be related directly theoretical molecules.